Hello, today's lesson is going to be on rotational forces in balance. In particular, how they apply to beams and moments. Now, what we're going to do is first of all define in physics a quantity that represents the amount of rotational effect that a force has about some point at which rotation may occur. And we call this quantity torque, T-O-R-Q-U-E. Let's just highlight that now in your notepacks. Torque. We'll use any colour, but I'll choose green. Now, to understand the factors that affect the size of a rotational force, let's consider a series of three diagrams. The first one here shows a spanner being pulled leftwards by a hand. The force is shown by an arrow. Notice that the arrow is a certain thickness, and in the diagram below it's shown as a larger or thicker force arrow. In a moment we'll look at that. And we'll also notice the distance at which the force is applied from the point at which rotation is likely to occur. In this case, the bolt that the spanner is connected to. And the amount of rotational effect is shown as a curved arrow, because you can imagine if this force were able to move the spanner, there would be a clockwise rotation about this point. And so we say a clockwise rotational force or a clockwise torque, T-O-R-Q-U-E. So the two factors involved are both the distance at which the force acts from the point of rotation and the size of the force itself. If we now consider a second diagram where the distance is the same but the force is greater, then it's not too much of a conceptual leap, it's not too hard to understand that the rotational effect will also be greater, again shown by a thicker arrow than in the first diagram. Now let's consider going back to the original size force, shown by a thinner arrow in the third diagram, but increasing the distance at which the force acts from the point of rotation. So a longer spanner is being used. And in this instance we see that there's a greater rotational force effect as well. So in summary, we can increase the size of the rotational effect by either increasing the size of the force or the length at which the force acts, the size of the distance. And so we define rotational effect or torque as the product of force times perpendicular distance from the point of rotation. And these are the two factors or two quantities that affect the size of the rotational force. It's important that we understand that the force, or should I say the distance and force, must be perpendicular to each other. Notice here the force in the first diagram is pulling to the left, but the distance is actually straight down vertically from the point of rotation, the center of the bolt, to the point at which the hand applies the force to the spanner. Now they have to be perpendicular because if you consider for a moment a standard piece of playground equipment, a sort of rotating platform or roundabout, where one person pulls directly outwards from the center of the circle, then there's no rotational effect. They're not pushing left or right at the point where they're pulling on the rotating platform. So no rotation occurs. The force isn't zero, and neither is the distance from the point of rotation, but still the rotational effect is zero because it's not perpendicular. If we have, in the second situation shown, the young child pulling on the rotating platform at some angle at which there is both a radially outwards component of force and a perpendicular component of force, the sideways or perpendicular component does have a rotating effect. So in this case, using the mathematics, we can see that the f sine theta, where theta is measured from the radius to the direction of force, the f sine theta component of the force F, acting at a distance r from the point of rotation, produces the torque. If I were to write down an equation that represented the total amount of rotational effect that this force has, it would be f sine theta times r for this particular situation. So in summary, once again, it's force times perpendicular distance that gives the total turning effect or torque of a force, and it could be either clockwise or anti-clockwise. Now, how does this help us in problems involving forces? Well, to solve problems, we need to do the following. First of all, we choose a point where we're going to consider rotational forces about. And we'll talk more about this in our first question. And then we look at the idea that the sum of the forces acting have to balance. So the total upwards and downwards force, as well as both the total leftwards and rightwards forces, must equal. And importantly, and this is the point here, the sum of the anti-clockwise rotational effects, or torques, sometimes referred to as moments, must add up to the sum of the total, or the total of the clockwise moments. So it's this highlighted point here that really helps us as something new when we're doing these types of questions. So what I'm going to do now is take a short break, and we'll come back and have a look at our first example and how these concepts can be used in a typical physics exam type situation. Okay, now this is our first example. It consists of a beam supported by two supports, which we've referred to as support A and support B. The beam itself has a mass of 30 kilograms indicated in the question, and therefore it will have weight. The weight will act right through the center of the beam, we assume in most questions, unless stated otherwise, which it won't be for Year 12, that the beam is uniform. That is, that the weight force acts right through the center of the beam. This beam is specified as having been 6 meters long, so we can assume that the weight force acts at a point which is 3 meters from either end of the beam, straight down, vertically downwards. So I'll highlight this force. That's the weight of the beam. The second force acting on the beam is the weight of a person standing 2 meters from one end. This person has a mass of 50 kilograms. We'll see how that translates into a weight of 500 newtons in a moment. So that person's also pushing downwards on the beam with a force equivalent to their own weight. And I've shown that as a longer arrow because it's a greater weight force for 50 kilograms as compared to 30 kilograms. Now, if these were the only two forces acting on the beam, what would happen? That's right, it would accelerate downwards, but it doesn't. So there must be other forces acting upwards on the beam to balance these two downwards forces. And since the beam is being supported by two supports, there are only two other positions where upwards forces can act. We don't know the size of those forces, but we'll represent them with arrows to help us visualize the question. The force, we'll do point A first, the force at which support A acts upwards on the beam is some unknown force. We'll represent that with F subscript A. We'll show that in the working in a moment. And at point B, we also have a force of unknown size acting vertically upwards, and we'll represent that with F subscript B. You may notice that I've shown this second force here as a shorter arrow than the first force. Now the reason for that is that the person sitting on the beam is closer to end support A, and therefore a great proportion of their weight will be taken up by support A. So we've shown that as a longer arrow. Now this is only really important in terms of conceptualizing the problem. When we do the calculations, we will see that it doesn't matter what size or direction we show these forces acting in, that the maths will automatically correct it for us if we make a mistake. For instance, if I showed the force acting downwards here, which would be ridiculous, then we'll end up with a negative value for that force when we do the mathematics, which will be telling us that it's in fact the other direction. And the size of the forces will come out automatically from calculations. But it's nice to try and anticipate the way things will go, because that way we can identify if there's been any mistake more easily to see if it matches up with what we expect. Okay, now Let's read the question, and as we do so, we shall refer back to the diagram to confirm the information in the diagram is consistent with that of the question, and also to help us understand what's actually been asked. This is a good practice in any physics question, or in fact in any question, whether it be mathematics, physics, chemistry, or even an exam question in English. It's a good idea to refer information written to any information provided in any other form. So here we go. A horizontal beam of mass 30 kilograms and length 6 meters is supported at 2 points underneath, points A and B. We see points A and B, we note the 6 meter length, and the 30 kilograms is information not shown in the diagram, but we'll show that in a moment when we write down the weight force here. Point A is 0.5 meters or half a meter from one end. Let's check that. There's support A, or point A, half a meter from one end. Yes, that's confirmed. And point B is 1.5 or 1.5 meters from the other end. Let's check that. Point B, 1.5 meters. Correct. A person of mass 50 kilograms stands 2 meters from the end nearest point A. There's the person. There's the 2 meters from the end nearest point A. Find the normal reaction forces at points A and B. These are the other forces that we already had the sense to mark in our diagram. Now, with this diagram in mind, let's see if we can solve the question.